Hello everyone. So in this video, I am going to discuss and design a dual edge flip-flop that transfers the data on both the rising edge as well as the falling clock edge. So SystemVerilog does have a edge keyword and it can be used to detect any change in input data in both the rising and the falling edge of a flip-flop. But it is generally used for high-level modeling and have some synthesis issues, especially when we are considering the FPGA libraries. Some ASIC libraries do support the edge keyword, but still, it is better to design dual edge flip-flop because it will be supported by both the FPGA and all the ASICs. So let's begin with the circuit diagram of the dual edge flip-flop. So here is the circuit diagram of a dual edge flip-flop. Here you can see that we are using separate flip-flops for both the edges. And let's assume that the upper one will be used for the rising edge and the lower one will be used for the negative edge. So here you can observe that we are distributing the input signal D to each of the flip-flops, and before assigning that value to the flip-flop, we are XORing the output of one flip-flop with the another's input. So for example, in the upper flip-flop, you can see that we are XORing the D input, and the second input for that XOR gate is the output of the another flip-flop. And same goes for the flip-flop here. After that, what we will do, we will take both the output of both the flip-flops and we will XOR them together and assign it to the major output Q. And I will help you understand that why we are using this design choices. So let's go back to our QuestSM and let's module our dual edge flip-flop. So here I will begin with naming our module. I will name it DFF and it will have one output. I will name it out and three inputs. Those are clock, reset, and the input. Now I will mention the data type and the direction of each of the signals. Each signal will be of single bit. So I am using the logic data type. And now I will mention the input. So as per our dual edge flip-flop diagram, we have to fed the output of one flip-flop to another and we have to XOR it with the input. So what I will do, I will mention two variables. The first one will be trigger 1 and the second one will be trigger 2. So I will assign it to output. So what should I assign? So let's hop back to our diagram. So suppose this is the trigger 1 and this is the trigger 2. So here we can see that the output is being fed the XOR between the trigger 1 and the trigger 2. Similarly, like here we can see that the output of other flip-flop, which is trigger 2 in this case, will be fed to this flip-flop, and before that it will be XORed with the D input, the major input. So let's go back to QuestSM. So I will just do the XOR between trigger 1 and trigger 2. Okay. Now I will write the always block for each of the flip-flops. I will use always FF. So my first flip-flop should be triggered during the pause edge of the clock. And for this design, I am taking the positive edge trigger reset. So if reset is high, then the trigger 1 should be equals to 0, else trigger 1 should be equals to the XOR between the input as per the diagram and the output of the other flip-flop, which is trigger 2. So we will just do the same thing for the other flip-flop, but for this flip-flop, we will be assigning the output to the XOR between the input and trigger 1 to trigger 2, and it will trigger in the neg edge of the clock. Our reset remains pause edge. So if the reset signal is asserted, the trigger 2 will get 0, else trigger 2 will get the XOR between the input and the trigger 1. So this concludes our design for the dual edge flip-flop, and I have specified everything as per the diagram. So I will explain you what will happen right here. So first, I will check for any typo or any compilation error. Okay, the code is fine. So what is happening right here? So there will be 4 cases. So each of 4 cases are categorized into 2 cases. So the first case category is that the input remains stable during both the pause edge and the neg edge. So suppose if the input is 1 in the pause edge, then it remains 1 in the neg edge. And similarly, if input is 0 during the pause edge, then it remains 0 during the neg edge. So these are first 2 cases for the first category, and the other 2 cases lies in the second category. That is, the input is transitioning during the edges. So let's say the input was 0 during the pause edge of the clock, then in the neg edge of the clock, input transitions to 1. So our flip-flop design should be capable of detecting that change and assigning it to the output. So I will show you how it will work. So let's consider all the cases. So for our first case, okay. So So first I will mention the stable category. So in stable category, let's say the input remains 0 for both the edges of the clock. So it remains 0 at the pause edge of the clock and also at the neg edge of the clock. So what will happen right here is that first we will begin with the positive edge flip-flop. So after the reset, after everything is setted, then the input, the XOR between the input and the trigger 2 will be assigned. So right here, the value of the trigger 2 will be 0 and the value of the input is of course 0. And the XOR between 0 and 0 will be 0 and it will be assigned to trigger 1. So then during the passage of the clock, the same thing will be passed out to the output after it detects changes to one of its uh, input. So here what will happen that trigger 1 will be given the XOR between the input and the input is 0 in our case and the XOR of trigger 2 and trigger 2 is 0 by default. So trigger 1 will get 0 and in the same time the output will get the XOR between trigger 1 and trigger 2 and both the trigger 1 and trigger 2 are 0. So output will just get the XOR between 0 and 0 which will be equals to 0. So this is what will happen during the passage of clock. I will mention it. Now in the neg edge of clock. So first observe that we were successful in passing the value, the exact value of the input, which is 0 to the output. And this is the functionality of D flip-flop. It just passes whatever the value it is in the input to the output. So in the next edge of the clock, which is the neg edge. So in the neg edge of clock, what will happen? We will go through this flip-flop and trigger will be assigned the XOR between input and the trigger 1 and both input and the trigger 1 is 0. So it is obvious that the trigger 2 will get 0 and when the trigger 2 is 0 the output will again assign 0 to the output because it will be the XOR between 0 and 0. So this was the stable case in which the value of input is 0. So let's move on to our next case in which the value of the input is 1 and it remains 1 in both the edges of clock. That are the neg edge, the pause edge and the neg edge. So what will happen right here is that trigger will trigger 1 trigger 1 will get the XOR between the input and the trigger 2. So what will be the value of input? It is 1, which we have already declared. And the default value of the trigger 2 will be 0. So it will be just the XOR between 1 and 0, which equates to 1. So as per the characteristics of XOR gate, if the comparing inputs differs with each other, the output will be 1, and if they matches, then the output will be 0. So the trigger 1 will generate the output. The trigger 1 will get the value of 1. So what will happen with the output? It will just get the XOR between the trigger 1 and the trigger 2. And right now, as you can see right here, that the value of trigger 1 is 1, and the value of trigger 2 is the default value, which is 0. So it will just get 0. So after getting this, the output will be assigned 1. So once again, in the posage of the clock, so this happened in the posage of the clock, by the way. So once again, we were able to pass the correct input to the output, and you can see that the XOR between 1 and 0 will be 1. And let's see what will happen on the nag edge of the clock. So in the nag edge of the clock, the trigger 2 will be assigned with the XOR between input the and the trigger 1 signal. So both the input and the trigger 1 signal are 1 in this case. So it will perform XOR between 1 and 1, which will be equals to 0. So since trigger 2 equals to 0, again the trigger 2 does not change, and the output will again do the XOR between trigger 1 and trigger 2, which is the XOR between 1 and 0, which again equates to 1. So this was the scenario in which the input was stable for both the rising edge of the clock and the falling edge of the clock. And I have demonstrated the scenario for both the possible inputs. So now let's move on with the toggling input. So our second category is toggle or changing, whatever you want to say it. So let's say for our first case, the input is equals to 0 at the posage of clock, or I will just write posage. So input is equals to 0 at the posage of clock, but at the nag edge of clock, the input changes to 1. So it is toggling between both the edges. So how will this flip-flop perform and give the output in such scenario? Let's find out. So again, let's begin with the trigger 1. So trigger 1 will get nothing but the XOR between the input signal and the trigger 2 signal. Here, first we will be looking through the posage of the clock. And in the posage, the value of input is 0. So it will perform the XOR between 0 and the trigger 2, and the default value of trigger 2 is also 0. So the XOR between 0 and 0 will be equals to 0. So what output will do? It will just perform the XOR between trigger 1 and trigger 2. Trigger 1 here is 0, so it will get 0, and trigger 2 is obviously 0, so it will again perform the XOR between trigger between 0 and 0, and we will get 0. So we successfully passed the correct input to the output. So let's find out what will happen at the nag edge of the clock. So let's write nag edge. So in the nag edge of the clock, the input is transitioning from 0 to 1. So the input will be 1. So in the nag edge of the clock, the block containing the trigger 2 will trigger. So trigger 2 will just get the XOR between the trigger 1, and here you can find the pause edge of the clock. The value of the trigger 1 was 0, and it will perform the XOR between the trigger 1, which is 0, and the input, which is 1. So when this happens, trigger 2 will get 1. So when trigger 2 will get 1, the continuous statement right here will detect the change in trigger 2 and it will trigger. So what it will do, it will just assign the output with the XOR between the value of trigger 1, which is 0, and the trigger 2, which is 1. And the XOR between 0 and 1 is 1. So once again, even though the input changed in the nag edge of the clock, our particular design will be successful in transitioning the data correctly. So let's move on to our final case in which the input is 1 initially at the pause edge of clock, and then in the nag edge of clock it transitions from 1 to 0. So let's find out what will happen first at the pause edge. So first in the pause edge, trigger 1 will trigger, and it will be assigned with the XOR between the input signal and the trigger 2 signal. So since the by default the value of the trigger 2 will be 0 and the input is 1, so the XOR between 0 and 1 will be 1. So output will get the XOR between trigger 1 and trigger 2, which will be again the XOR between 1 and 0, which will be equals to 1. So it transitions the correct value at the pause edge of the clock. So let's find out for the nag edge of the clock. So at the nag edge of the clock, the input transitions from 1 to 0. So here the trigger 2 will come into action. So the trigger 2 will be assigned with the XOR between trigger 1 and the input. So the trigger 1 is 1 and the input is 0, and the XOR between 1 and 0 will be 1. Then on the same time, the output will perform the XOR between trigger 1 and trigger 2. So here you can see that at this point, both the trigger 1 and trigger 2 are 1. So it will just perform the XOR between trigger 1 and trigger 2, which is 1 and 1, and we will get 0. So once again, when input changes to 0, we were able to transition the correct value to the output. So this was the functioning of a dual edge flip-flop, which triggers in both the pause edge and the nag edge of the clock. And this particular logic is purely synthesizable, and any FPGA library will support it, and every ASIC library will also do the same for it. So I hope you find this video useful. Thank you so much and stay tuned for more.